So we're going to look at geometric shapes and figures and how they occur in everyday life and also in art. So here we have a picture of the Mona Lisa, a very famous painting. A lot of people believe that part of the beauty from this painting comes from the fact that the artist used the golden ratio. And so the golden ratio can be represented by a rectangle. And we actually have a rectangle here. That's in the ratio of 1 to 1.618, about approximately. And so I wanted to check to see if that was actually true. And so what I did is I just made a little gray rectangle in Paint, and I just made it 100 pixels by 162 pixels, which is the same ratio. And so I've got that rectangle here, and I'm going to try and see if I can fit it so that it fits around the face as they say it should. So if I move the rectangle around, okay, it looks like I got to make it a little bit larger. As I'm sizing it, it's keeping the same ratio between height or length and width. So the ratio is not actually changing, even though the rectangle is growing and shrinking. And so I would say that that is correct. I can probably do a slightly better job. Let's see. Yeah. So that looks like about the correct ratio. So we call that the golden rectangle. So the other thing we're going to look at are called tessellations. Tessellation is a pattern that fills a flat surface. Okay, we call this flat surface a plane. And when we fill the plane, we say we're tiling the plane. Okay, so oftentimes you'll see this in clothing. Here's an example. Here's another very famous example. This is actually called houndstooth, and you'll probably recognize this from somebody's scarf or pants or shirt or something. And you can see that the pattern repeats itself over the plane. It tiles itself. Here's another example using hexagons and triangles. You can see that it's repeating itself. Here we're just sort of changing the color of the hexagons and just continuing to use the same polygon. Here we have a combination of squares and triangles. Now if you look closely, you'll probably notice that the triangles and the squares have the same side length. Otherwise they wouldn't really touch and sort of connect to each other and tile. Here we've got arrows, and the person here has chosen to sort of vary the color scheme, but everything is an arrow. So in this example, we no longer have straight lines, we have curves, and you can kind of see it goes up and it goes down and it goes left and it goes right, so it's kind of like a square. And in this example, we have a much more complex image and no longer have any straight lines. So there's a lot of possibilities when you're tessellating a pattern. Cell phones are really small radios that communicate with towers connected to the telephone system. The towers in an urban area must be placed close together because cell phones are low-powered, typically 3 watts, and have a limited range. Also, each tower only offers a limited number of frequencies, about 800, restricting the number of calls that a tower can handle at one time. In an urban area, towers are placed about 5 kilometers apart. Each tower is thought of as the center of a hexagonal cell as shown. Consider an urban area that measures 20 kilometers on a side. Draw a tessellation using hexagons and show how many towers are needed to service the cell phone network. So I'm going to assume that the area is a square. And what I've actually done is I've used a tool that I found online, and you're also going to use it. And it just allows me to place geometric shapes on the screen to create a tessellation. So if each one of these are 5 kilometers apart, so let's say from here to here is 5 kilometers. Here to here is not quite 5 kilometers, but let's just say it's a little less than 5. So 5, 10, 15, 20, and then I added one more just to make sure I reach the 20 kilometer mark. I did the same thing in this direction, so these are 5 kilometers apart, so 5, 10, 15, 20, okay? And I just kind of rounded it out to make a somewhat of a square. And when you count all of these up, I got 15, 12, and 27 hexagons.